my name is Anastasia Chavez. I'm currently a postdoctoral fellow. My official title is an NSF and a President's Postdoc Fellow at UC Davis, working under the mentorship of Jesus de Loera. And I was asked to give a 20-minute intro talk to undergrads about something. And I've been recently thinking a lot about a connection between something called a convex polyhedral cone and then another thing called cycles on graphs. And these are the two objects that I chose to introduce to you today. So I posed this question, what is a cone? You can't see it. If you come and look on the computer screen, there's a nice colorful image of, I think they're unicorn ice cream cones. And I put this here because I imagine, when you Google cones, or if you were to ask my two young kids what a cone is, you would end up with a lot of different answers to this question. They might say a cone is something you put a scoop or 2 scoops of ice cream into. But the kind of cones that I'm interested in look more like this. So this is an example of this thing I'm calling a convex polyhedral cone. I'm going to give an intuitive idea of what this type of cone is. From here on out, I'll most likely just use the word cone, but when I say that, I'm thinking about these types of structures that are using some finite information to generate them, so you'll never end up with curves in these cones. They'll always have some nice edges and corners. And then I will present to you two different descriptions, one in terms of vertices and rays, and the other one in terms of something called a hyperplane. And then end on this application that I just mentioned that links these cones with graphs. And then I added a little bonus at the end, so I'll leave that as a surprise. Okay, so first, what's this intuitive idea of a cone? So if someone was to stop you on the street and just say, hey, I'm a little confused, can you give me a sense of what a cone is? Here's your quick answer. You could say, well, it's just a set of vectors closed under positive combinations. Right, well, I don't know if that's going to be super helpful to the layman on the street, but to someone interested in math, they might be piqued by this. So what does that mean exactly? Well, I'm going to give you a set of points in space, and these are going to be points in R2. The points 1, 1/2, 1, 2, 2, 1, and 1/2, 3 fourths. And I'll represent them as vectors in R2. So you can more or less see these vectors. I don't know if this helps at all. Let me see if I can change this a little bit. Do this. Okay, so oh, there we go. I think that works. Okay, great. So we have these 4 vectors here. One vector representing the vector emanating from the origin to one of those points in my set. And what I said is I want to take these positive combinations of all our vectors. And if I do this, the formula that I would write would look like this. I'm just letting coefficients range over all the positive real numbers. And then I'm going to take this linear combination of all the vectors that you just mentioned. And when I do this, what you'll have to use your imagination for is it generates this space in between the two outer rays. This is supposed to be blue. Okay, so imagine that there's this blue space in here. So you're actually generating all the points that lie within that orange ray and that blue ray extended out into infinity. Okay, so that's your intuitive idea of what a cone is. So more or less it's cones as we think of them. All right. So to give a more concrete description of this, we're going to take sets of vertices, and we can also include rays, so some infinite line in space. And then we're going to, again, take this positive combination, this positive linear combination over these vertices and rays. And the picture you want to keep in mind is this one. Again, there should be some blue shading in between those dotted lines there. Okay, so we have one way that we can generate this cone. Another way to generate these cones is in terms of intersection of half spaces. Okay, so to get to what a half space is, first let's just define what a hyperplane is. So in 2 dimensions, a plane is just going to be a line. In 3 dimensions, a plane is this 2-dimensional subspace. In general, a hyperplane is just 1 dimension. It's a 1-dimensional, a subspace that's of 1 dimension less than your total space. So if I'm in n dimensions, then I want to look at all the subspaces that have dimension n-1. That's going to be a hyperplane. Another way to say it is that's the solution set for some linear map in your space. Now to create a half space, I'm just going to choose one side to that hyperplane. You can write it as the solution set that satisfies this inequality. I want all the things that are equal to 0 plus everything that's positive. Right? I've just chosen one side of that half space of that hyperplane. And one example here is if I take the line equal to 1/2 times x1 minus x2 equals 0, that's going to be this blue line. And then if I take all the stuff that's negative, you can't see it, but it should be everything above that blue line. I have a blue shading above that line there. So this represents a hyperplane, a half space. And then we have an orange line now that's given to us as 2x minus 2x1 minus x2 equal to 0. And then I want everything that's positive. So I take all the stuff to the right of that line. That should all be orange. So now we've got these two these two half spaces in R2, and I just want to take their intersection, and that's going to generate a cone for us. So again, use your imagination. There should be two half spaces here. The stuff in blue should go above the blue line. The stuff in orange should go to the right of the orange line, and then that picture would be everything between those two things is shaded blue. Okay, so I apologize for the lighting, but I'm making you work really hard today. Okay, but so what is the definition? It's exactly what I've said. I'm just taking a collection of closed half spaces, and I want to find all the points that satisfy when I'm on whichever choice I've made of that side of the hyperplane. That's exactly what my AX less than or equal to 0 is saying. I'm going to represent the half spaces as a matrix, and then I just want to take the solution set to that satisfies this inequality. Okay, so we've defined a convex cone in two ways. We've said I'm going to give you a set of vertices and rays. I can also say I'm going to give you a collection of half spaces, take their intersection. This should generate a cone, right, in either instance. And it's actually a very powerful theorem, thanks to Weil-Minkowski, that says these two are equivalent. So you can generate a convex polyhedral cone in both ways using this vertex ray description or the hyperplane description, and they're essentially the same thing. So when you think about these cones, you can think about them from two different perspectives, and depending on what you're using them for, one might be more useful to you than the other, one of these definitions. Okay, so just to give a flavor of where these cones can commonly show up, in questions such as a solvability of a general system of linear equations, so this is Farca's lemma, cones will pop up here. If you want to count the number of integer points in some space, this is something called Ehrhart theory. You can think about cones in that setting. Discrete optimization, linear programming, and feasibility problems, as well as computational complexity. So these are all areas like where cones are a very typical object that show up. So I wanted to give you an example of where it's not as likely when you think about this particular question in mathematics that you would say, well, how can cones be useful? And that's where graphs come in. So just a quick and dirty definition of a graph. We want to take a set of vertices, some points in space, and then we're going to take a collection of edges, which are just identifying 2 points together. One example of such a graph is this one here called the complete graph on 4 nodes, or K4. So we take these 4 blue dots, and then I'm going to label all the edges where I've identified every node or vertex to every other vertex in my graph. And even though you see edges 5 and 6 crossing each other, imagine that this lives off the paper. So it's actually in 2 dimensions. So these 2 lines are sort of hovering above each other. They don't actually intersect. So there's not a true vertex at where it looks like those 2 lines did intersect. Okay, so here we have this complete graph on 4 nodes. And we're going to define a cycle on that graph to be just a collection of edges that intersects just once. So we don't want to have a path in my graph that intersects more than one time. So basically like a circle or a loop, you can kind of imagine that's what you're forming in your graph. So an example of a cycle on K4 would be this one that's the shape of an hourglass. And since I said that our two edges in the center are sort of hovering across, we're not actually self-intersecting more than one time. Okay, so I've made like a true circle in this graph here. Okay, so now we're talking about graphs and cycles. So how do we get back to cones? Well, we can actually represent this cycle on the graph as a vector. And I'll define it in terms of something called an indicator vector, where the ith entry of my vector is going to equal 1 if I use that ith edge in my cycle, and I'll let it equal 0 if I don't use the edge in my cycle. So let's look at the cycle that we drew on the complete graph here, and I use the edges 1, 3, 5, and 6. So if I look at the vector, the indicator vector for this cycle, that means I want positions 1, 3, 5, and 6 to all have a 1 value. And since I didn't use edges 2 and 4, then the entry in position 2 and position 4 should be equal to 0. So here's a way to represent the cycle on the graph in terms of a vector. Okay, let me just pause real quick. I've been talking for a little while now, make sure there aren't any questions. Okay. Well, feel free to interrupt me at any point if you think of one. Okay, so now we've got vectors representing cycles on graphs, and that's enough information for us to now start thinking about cones. So I can actually write down all of the cycles in my graph as a matrix. So this first column here, that's the first 4 entries are 1 and the last 2 are 0, so that's positions 1, 2, 3, and 4, actually correspond to the edges 1, 2, 3, and 4 that go around my graph, which is another cycle. So every column in this matrix represents some cycle on my graph. And all the rows are indexed by the edges, so that's how you want to read this information from the matrix. And now that we've got this collection of vectors, in this case it's going to be in R6, we can think about cones as just positive linear combinations over these vectors in R to the 6. Okay, and that's exactly what I wrote here. I have a couple typos I meant to change, and I need to get to, this should be a 6. I want to take positive, so that should have a less than or equal to 0. And I'll just be, I guess, make sure I'm being totally honest. I'm saying positive. We are allowing there to be 0 coefficients, but so non-negative, I guess, technically. But you want to think about it in terms of just sort of the positive orthant that you're interested in when you think about generating these codes. Okay. So since this dimension is too high, I can't actually draw what this cone looks like for you, but I can sort of signify it in this way. So here's how you can write the solution set to this cone. And so why is this important? So now we've got a way to think about the cycles of our graph in terms of points lying in some cones. So how is that useful to us? Okay, so let's think about some open questions in graph theory. And this is sort of what's motivated me and Jesus to be thinking about this in the first place. So how is this useful? Well, there's a long-standing open conjecture called the cycle double cover conjecture. And what it says is if I were to hand you any graph, you should be able to, well, bridgeless, okay, I'll just make sure that there's no single edges that connect 2 larger graphs together. So if we take these certain kinds of graphs, I'm going to hand it to you. I'm going to say, can you find a set of cycles that covers all the edges of this graph so that any edge is found in exactly 2 cycles from your set? Okay, this conjecture says you should be able to do that no matter which type of bridgeless graph I hand you. Okay, so what is that really saying? Let me just break it down briefly. So if we take K4, it's saying I want to find a set of cycles that should cover all the edges of this graph so that every edge is found in exactly 2 of the cycles that I put in my set. So here's one cycle that we talked about on the previous slide. I'm going to keep track of it as that red box in the set to the right. And here's another cycle that's like a bow tie. in my graph. Keep track of it over there. And then, great, last is this hourglass cycle. So I've got these 3 cycles as my possible set. And another way to describe this, since I've colored all my cycles, is to say if you check any edge in my graph, it should be colored with exactly 2 colors. So you don't have to be different. They could be the same. But here, if you look at all the edges, they're only colored red and green, red and blue, or blue and red. So that means this conjecture, this cycle double cover conjecture, holds for K4. Okay, so this is stating that this should be true for any graph, but it's actually not known. But if we think about it in terms of the language of these cones, another way to say it is just if I generate the cone over all the cycles of my graph using just positive integers, then I'm guaranteed to find this vector of all 2's in that cone. So this conjecture is really asking for the presence of one vector in a cone, which I think is a really nice way to see how interpreting questions such as these ones in graph theory and using the language of these convex cones can be really nice, because we've taken a question in graph theory that seems a little complicated and just turned it into, can you find this point in your cone or not? And that's really what the conjecture is asking for. So in general, you can ask the same question. You can say, well, instead of all 2's, I'm just going to hand you any vector of positive integers. Does this thing lie in your cone or not? Okay. And so another way to say that in terms of the graph is, I'm going to take this vector of all positive integers. Can you find me a set of cycles where the ith edge is covered ui many times? Again, that's just asking for the presence of that vector in the integer into the integral cone over all the cycles of G. Okay, so hopefully I've convinced you that there is some importance in using this language of polyhedral, convex polyhedral cones in sort of non-convex geometry, geometric settings. But this is actually an example of sort of the types of things that I've been thinking about while I'm at Davis. In particular, we're sort of stepping away from, I'm not trying to prove the cycle double cover conjecture. It's been open a long time, and I don't know that anyone's close at all to solving this problem. But we can at least ask things about like properties of the cone of these cycles of graphs. And so we do have a result about the dimension, so how you can describe the dimension of this cone. And hopefully more coming. Okay, so if you're interested to learn more about this stuff, here are 3 references that I would suggest to you. They're the ones that I used in preparing this talk, and they're all books that I've read, or it's mostly read, and really enjoy. And with the last couple of minutes that I have left, well, let me just pause and make sure there aren't any clarifying questions or anything that comments people would like to say. Because here comes the surprise. So I thought I would just mention a little bit about myself. I'm a born and raised Californian, far away from home. I miss my family. But I started off at the Santa Rosa Junior College. So Santa Rosa, I grew up, is about an hour north of San Francisco. And when I went to the junior college, I actually wanted to be a journalism major, and had kept up with math and done fairly well. And when it came time to think about college, I was encouraged to pursue a math degree and not a writing degree. And the guy basically told me, you've got good grades in math. You can do anything with math. You should just go get a math degree, and if you want to write, you can do that later. And I followed his advice, and pretty much that was the advice I got the whole time. It's just keep going. You're doing pretty well. And then I just kept getting degrees. And so at some point, I was getting a master's degree at SF State. I got both my bachelor's and master's degree there, started a family and got married. And it was really when I had my 2 daughters that I realized part of why I really enjoy math was not only to think about puzzles and to stay engaged and thoughtful and discovering things, kind of like Sudoku, on steroids, but also was to be in a place where I felt like I could really make a difference. And once you have a PhD, I kind of felt like that was the certificate that made people had to stop and listen. And so that was another reason why I finally decided to go to graduate school, not only because I really enjoyed the math that I was doing as a master's student, but also I felt like I really wanted to be in a place where I could, give back to the community and to be a mentor, which I felt like we're in grave need of. So I ended up going to UC Berkeley, finished there a couple of years ago, and the future is sort of still unknown. I'm finishing up my doctorate degree and not quite sure what's coming next, but having a really good time along the way. And just wanted to end by saying, I guess just a plug for continuing to come to events like this. This is actually my first time coming to the Field of Dreams conference, but I've been to a lot of other conferences that have the same supporting undergraduate and supporting underrepresented minorities. And I was thinking back to when I attended one such conference called SACNAS. Hopefully you all have heard of it, and if you haven't, definitely look it up. I heard it's going to be in Hawaii next year, so see, yeah, maybe that's a good time to go. But so it was through that conference where I met a woman who ended up being someone who hired me on as a graduate student TA for an REU, where now I get to see the students that I mentored in that REU graduating from PhD programs, and one of which is finishing up at UC Berkeley now. So it's just pretty amazing to see, over the long term, the kinds of connections that you can make at events like this and how they can really impact your life and the people around you. So I'll just end on that, and thank you so much for your time.